Well, it's my privilege to introduce Henry Pohl today. Henry has been a long-time colleague of mine, working in the early days of Apollo and Shuttle. He's an old country boy, but he has been he has created more innovative designs on technical problems than anybody I know, and we'll try to bring some of those out, because he's really created some very innovative solutions to technical problems. And I'm going to set Henry up a little bit, so let me set the stage for you a little bit. I was manager of the Space Shuttle Orbiter, and the engineers came to me and said, Aaron, the waste management system on the shuttle is not working very well. Now, the waste management system, in simple terms, is the toilet. They said the toilet's not working very well, and we really need to go off and design a new toilet. So, you know, I thought for a moment. I said, well, yeah, that's probably a pretty important thing to do. So we did. Well, it turns out the original contract, and I'm quoting a little bit from memory, was about $10 million. Now, $10 million for a toilet, when you can go down to any place and get a toilet for a couple of $100s, is a pretty high number. But that wasn't the worst of it. The worst of it, about 6 months later, they came to me and said, Aaron, guess what? It's not $10 million, it's $20 million. So Congress got wind of this. Congress got wind of this, and they wanted me to come up and testify. And you can see what kind of fun they're going to have. Waste management, you know, they're going to really have fun with this subject. And you may know some people in Congress, but the name was Mr. Sensenbrenner from Wisconsin. I remember very clearly. He's still in Congress now. He was head of the Science Committee, and that's who we had to go testify before. Well, there was a reporter. There's a reporter for the Washington Post. Her name was Kathy Sawyer. Now, Kathy was the science reporter for the Washington Post. Very, very good. Kathy was very smart, very fair, but she really bore in on things. So Kathy got wind of this. So she wanted to publish an article on it. So she called me, and she said, "Would you please talk to me about the waste management system?" I said, "Boy, she's going to get me in trouble." So I said, "I tell you what, I've got somebody that can really tell you about the waste management system, and I'll have Henry Pohl call you." So I talked to Henry about it. Now that's going to be Henry's introduction to this class of what he told Kathy Sawyer, because it's a classic. Henry, it's all yours.
Testing.
It's on, but I don't see the light on, so maybe the battery is bad.
Want to use this one?
Okay, if you take that out.
Can you take it off up here? I can't see it. That just pops right up. Okay. Yeah, maybe something's loose. Short somewhere.
Now that light, before that light wasn't on.
Now you want to turn this one on, or it's on already?
It's on. Yep. It's on.
Okay.
Okay, set to go.
Okay, is it working now? Yep. Okay. Darren almost forgot about Kathy Sawyer, but okay. Kathy called me up and said, "Can you explain to me how I might explain to my neighbor's 14-year-old daughter why NASA has spent $10 million building a toilet?" Pardon me. And I said, "I'll try." And I thought for a little bit, now how am I going to start out on this? I said, you know, if you take the commode that you've got in your bathroom and you bolt it upside down in the ceiling, now try using it. I said, that's really a little better situation than we have on the orbiter, because at least we know which way the gravity field is on that. In orbiter, you don't know. Most of the time you don't have any, but it might be to the right or left or up or down. You know, that was the only reporter that I ever talked to that put everything down verbatim of what I said, the question she asked, and what I said, and printed that article in the newspaper. but that kind of sets a stage for operating in the absence of gravity. You know, I explained to her that the Space Shuttle volume that the people have to live in is about the same volume as you have in a modern bathroom. You know, if you look at the bathroom with a shower and the room out just outside of it with a sink and everything, we have just about that same volume in the shuttle. Now you seal that all up. You got a certain amount of air that you can use in there, and you only have the air to replace gravity. You've got to have a flow of air to direct whatever you want to direct in a certain direction. So you use that air, you run it through, you've got to deodorize it, you've got to clean it, you've got to run it back into the cabin almost instantly, otherwise you pull a vacuum in the cabin. And so whenever you start putting all of that equipment in there and all of that stuff in there on something that has never been done before, $10 million or $20 million is kind of cheap. When you get right down to it, you look at the number of people that'll hire for a year working on it, is cheap. But to try to get that message across is not easy. Go ahead and give me my first slide. Let me just tell you another one, since Aaron got me off on a tangent here. Chicago Tribune called me one day when we had a problem on Shuttle, and she was bad-mouthing Shuttle, and all she wanted to do was get a comment out of me that I agreed with something that she said so she could quote it. And I said, I don't agree with you. I said, you know, that Arbiter is really a pretty good vehicle when you look at what it has to do. I said, you realize when it's in orbit, it's going 8 times faster than a bullet when it leaves the muzzle of a 30-06. Silence on the other end. What's a 30-06? Well, I knew that wasn't a good example. But I told her, I said, that's a rifle, a military rifle that's used in the Second World War. And I used to fire that thing in the desert, and I could pull a trigger and see that bullet hit the ground out there 300 yards almost instantly. Now that shuttle's going 8 times faster than that. And I could see the headlines in the Chicago Tribune. The shuttle flies 8 times faster than a bullet. Long silence. She said, you know, maybe I ought to find something else to write about. I said, why? She says, I don't think I have a story here. Well, it wasn't a story because it wasn't negative. So Kathy Sawyer was the only time I ever got a good story from the press. I want y'all to feel free to ask questions. I'm here more to talk about what you're interested in talking about than my thoughts. So feel free to ask questions anytime. I would like to talk about a half an hour, so somebody's going to have to tell me when half an hour is up, and then I'd like to have some time for some questions. My first involvement in the space shuttle was Max Fauché kind of came up with this idea of a winged vehicle going into space, and we kicked it around for a while, and he formed a little committee, very small, about 20 people as I recall, put the people in a room. He wanted to keep it quiet, he wanted to keep it secret until he got enough data so that he could know whether it's feasible or not. Well, they wanted me to send the best engineer I had over there, and he appointed a guy by the name of Jim Chamberlain to head up that group. So I sent a guy over there. They closed the doors, had a guard in front of the door so nobody could come in, no information could get out. On the 3rd day, Jim Chamberlain called me up and said, I need to have a talk with my engineer. I said, why? He said, he balked. I said, what do you mean he balked? He says, Henry, you know what an old mule does when they balk, don't you? I said, yeah, they won't go. He said, well, that's you, Mr. Kendrick. He won't go. So I called up my engineer, and I said, what's going on over there, Darrell? He says, oh, they don't know what they want. He said, they gave me some requirements. I designed them an RCS system for it. They gave me another set of requirements. I designed another RCS system. they gave me some more different requirements. I designed them a different RCS system, and then they came out with another set of requirements. I'm just going to wait until they decide what they want, and then I'll design them an RCS system for it. Well, what he didn't understand was that's the way you go about setting the requirements. You get a small group of people together, you set down a set of requirements, you try to put a vehicle together, and see where it punches out. Usually weight, CG, something. So you change the requirements up a little bit and you design another system. You do that very quick, and you look at where that one punches out. And then you change the requirements again, and you look at those requirements and where it punched out, the first requirements where it punched out, you change the requirements a little bit and see where it punches out. So very, very quickly you run through very, very many configurations. That got the shuttle started. After it got started, we kept changing the requirements as we went through the program. I would suggest that you understand your requirements very, very clearly, and the impact of your requirements very clearly. You know, things like fail-op, fail-safe, or fail-safe, fail-safe, fail-op are very, very good buzzwords. But unless you really understand the impact of those, they can actually make a system less safe. I can make a very good case, and go ahead to the next slide. I can make a very good case that a 2-engine airplane is safer than a 4-engine airplane, simply by the way that you set your requirements. You know, FAA has a requirement that an airplane has to take off with 1 engine out. If you've got a 2-engine airplane, then most of the time you got 100% more power than you need. If you got a 4-engine airplane, you only got 25% more power than you need. Most airplane crashes are caused from lack of power at the right time. You know, if you've got the power when you need it, then you can get out of most bad situations. Our original requirements on the shuttle, after we got that started, was to keep the operations cost low. We wanted to keep the maintenance cost and the operations cost low. We initially were looking at oxygen-hydrogen systems. In fact, all of the early orbiters had the hydrogen and oxygen on board. In place of payload, we had hydrogen tanks and oxygen tanks in there and carried the hydrogen and oxygen on board. And we actually looked at using the hydrogen out of those tanks. You get it free to power the OMS and the RCS. And we looked at all kinds of ways of getting the pressure up high enough to be able to use the residuals to power the vehicle.
One of the students asked a question the other day, and we didn't give her a very good answer. I think that we did at one time look at putting the hydrogen in the payload bay of the shuttle. And that was one of the
all of the very early configurations of the shuttle had the hydrogen and the oxygen in the shuttle in place of payload bay. That was the very early configurations. Later on, as DOD got involved and other people wanted big spaces and carrying Greyhound buses up there and things like that, we had to use that space, and that's when we came up with the external tank, and that's when we came up with a side-by-side configuration on it. That's the way I recall it. But we looked at oxygen and hydrogen, then we went to methane, because we were looking at bulk density so that we had smaller tanks and smaller volumes. Then we looked at oxygen and alcohol, and I really thought we had a good system with oxygen and alcohol. I had a lot of confidence in that system. We used it on Redstone. My first job was working on Redstone. I really liked alcohol. I thought we had developed a good ignition system for the RCS, so we didn't have to worry about the thousands of starts. But obviously that was going to cost us money, and cost a lot of development money. And as time went on, we changed from having low operational cost to low development cost. And when we went to low development cost, then we went to bipropellant on the OHMs and initially to monopropellant on the RCS. And you go ahead and give me the next slide. Bipropellant, I say bipropellant, what I mean is storables, monomethylhydrazine and nitrogen tetroxide, both are storable propellants. It's self-igniting, so you don't have to have an ignition system for it. That simplifies the design a whole lot. We had a lot of experience with those propellants on Titan II, on Agena, and on Apollo. All of the Apollo stages used either Aerozine 50 and nitrogen tetroxide or monomethyl hydrogen nitro. So we went to that. On the RCS, we initially went to hydrazine as a monopropellant because it was the simplest system, the cheapest system, but very quickly the weight got out of hand, and we had to go to something that had a little bit more performance than hydrazine because all of that weight was in the back end of the vehicle, and the back end of the vehicle was getting too heavy. If you only remember two things out of this program, out of this exercise, and what I have to say today, the two things I want you to remember is that it is just not natural to think in terms of the absence of gravity, and it is not natural to think in terms of the absence of pressure. You know, when you think about it, you live in it around here on the ground. It's so natural that it's hard to think in terms of designing systems and the impact that the absence of gravity has or the absence of pressure has on the design of the systems. The other thing I would like for you to remember is that there is no substitute for a good, well thought out test program. Let me give you the OHMs as an example, and you can go ahead to the next slide. We did not have a vibration test program on the propulsion systems, on the OHMs or the RCS in the program, because by that time we had good structural programs. We could analyze the effect of vibration and stress on the vehicle. But we had a good propulsion test program. And we built an OHMs pod, just like the ones we're going to fly on a vehicle for qualification. And when we got through with all the propulsion tests on it, and we went through that program in a breeze, we had no problems at all with it. So we finished it early. We took that pod down to JSC. We put it in our vibroacoustic facility. And while we were running the QVVT, the low-level vibration test on that pod, just to get the response of how things responded to everything, the helium bottle fell out. 5 minutes after that helium bottle fell out, every structural guy in the world could tell you it should have fell out. It would fall out. But nobody thought about it in advance. What happened, we had taken high pressure line, helium line coming out of the bottom of the tank and going 5 feet or 8 feet over to the structure and bolting it to the structure over there. Now that thing was, when you started shaking it, that was acting as a torquing element on that tank and torquing that tank this way. And the struts that they had coming down holding the tank, it was fatiguing where they were put onto the tank. It fatigued them right in there and broke them off very quick. But we didn't pick it up. The OHMs was very, very straightforward from a development standpoint. We came out with a platelet injector that gave us very good combustion, very close to. Okay, platelet injector is one where we used photographic techniques to etch holes in the injector. You could get a very, very fine pattern. You made it in very thin sheets, and you coated the sheet with a coating where you could put them in a press and heat them and glue them together. So you came up with an injector design that was made out of many, many thousands of of very small, very thin plates that set up the manifolding on it. Normal injectors, you know, you drill out a manifold in the back, and then you take the face plate and you have to drill holes in it. And the problem we get into when you start doing that is with these very small drills, they tend to warp, or walk, or bend, and you don't get a straight hole, you don't get a good spray pattern. With a platelet injector, we could get a very close match. We could just kind of dribble a fuel in there and oxidizer in there where it always matched real good. We got very high performance out of it.
So that they know what we're talking about.
Oh, okay.
The injector up here where you have the
Fuel and oxidizer.
fuel and
coming
oxygen, and then you have to have a whole bunch of holes in a pattern such that the fuel and the oxidizer are properly mixed when they ignite inside.
You need to get the oxidizer to impinge on the fuel very precisely, so that with an earth storable propellant, a hypergolic propellant as we call it, that's self-igniting. And basically what you have is when the two fuels come together, it's like having a very strong acid and a very strong base coming together. The first reaction that you get is a heating reaction. That chemical reaction that you get will take the propellant temperature up to 800, 1,000, 1,200 degrees. Anyway, it gets it up to the combustion temperature, and then you start the combustion process. So you don't have to use any other ignition source. All you do is bring those two propellants together, and you get that chemical reaction that provides the energy, the heat, to heat the propellant to the combustion temperature. We had like all high-performance rocket engines, we had a stability problem with the ohms, and we had to put big acoustic cavities all the way. 38% of the injector on the ohms was cavities designed and sized to damp out the stability. So we had a very good, stable engine. The RCS, on the other hand, is a totally different design. Now, we put the propellant tanks on the RCS up in front of the ohms tanks so that for aerodynamic purposes. That gave us a 30-foot propellant line down to the RCS. Then we manifold 3, 4, 5 engines on the end of that pipe that's pulsing in and out of phase or steady state. Some of them are running at 40 milliseconds or 80 millisecond pulses. Some of them may be running at 4 times that on a pulse width, and some of them may be running at steady state. Anyway, the dynamics, the pressure in that line that the engine sees varies somewhere between vapor pressure and about 1,000 psi. And since one propellant is 1.6 times the density of the other propellant, when that valve opens down there, that pressure wave's got to go back up to the tank and come back down to the injector before you get basically any flow out of it. Just the compressibility that you have in the pipe will come out. So the pressure essentially drops to vapor pressure. Now we use helium to pressurize those tanks. Well, when you use helium to pressurize those tanks, the helium is dissolved in the propellant. When it gets down to the engine, it comes out of solution. So the engine has to be able to stay together at any mixture ratio and almost any pressure. And you're looking at hundreds of thousands of starts over the life of one of those programs on one of those engines. And we talk about pulse width. Pulse width is the on time, the minimum on time that you can have on a rocket engine. Now there's a volume between the face of the valve and the face of the injector that we call dribble volume. That volume, the larger that volume is, the larger the pulse width you need on it. You would like to have the seat of the injector to be the face of the, the seat of the valve to be the face of the injector, so you had zero dribble volume in there. That way you'd get closer to a square wave pulse. And your friends in guidance, control, they always want a square wave pulse. And they want it of an infinite thrust level and zero width, so that you put an instantaneous pulse. It makes it easy for them to calculate where the vehicle's going to go. Then if you get one that builds up kind of slow and goes down kind of slow. So the dribble volume, the volume that you have between the valve seat and the injector face, when the engine shuts down, when the valve closes, that flow stops, and that amount of propellant stays in there. Now, in a vacuum, when it gets down to the vapor pressure, it starts boiling out and goes out through the chamber. And you have a refrigeration effect from that boiling of the propellant. If the pulse width is too short, then the refrigeration effect will overcome the heating effect from that short pulse, and you keep reducing the temperature of the hardware. Now, the colder the propellant gets, the more heat that you have to put in the chemical reaction when it first comes together to get it to ignite. So you get an ignition delay in the thing, and then you start getting into hard starts if it gets too cold. So we set our pulse width on the shuttle at 40 milliseconds. That was the neutral point at which the refrigeration effect equaled the heating effect from the pulse, and so you'd maintain the temperature. We later on went to 80 milliseconds on it because we added the verniers. That gave us a little bit heat input.
It's a pretty tough design in itself, isn't it?
The valve that we used for a 1,000-pound rocket on the Arbiter weighed less than the valves that we used on the Apollo program for a 100-pound thruster. And what we did, we went to a pilot-operated valve, and that was kind of my concept that I borrowed from Sears Roebuck. If you ever take a washing machine apart on Sears Roebuck and you look at how the valve is designed, it's a pilot-operated valve, and they use the water pressure to open the valve. Well, I thought that was a good way to go. You put a very small coil in there, and quick-acting coil, and replace that rubber bellers that they used on Sears Roebuck washing machine with a stainless steel diaphragm, and you got it made. Well, unfortunately, the water pressure in a house doesn't vary as much as the water hammer does on the space shuttle. So before we got through with the design of that valve, it got to be a very complex valve, and it was a very expensive valve, but it works. Let me...
Probably the other thing that we ought to say about designing any system that's going to work with these hypergolic fuels, I mean, they just eat away at things like O-ring seals, and I mean, it's just nasty stuff, and so you've got lots of, in addition to the mechanical problems that Henry was talking about, you've got all the materials problems, which just makes your life harder.
We really wanted to stay away from hypergols, from the acid, from the very strong acids and the very strong bases, for the simple reason that there's very few materials that's compatible with them. Matter of fact, the main reason we went to a hydrazine RCS in the beginning was to avoid having an expulsion system in the oxidizer, because we had no material available that you could put in there as a diaphragm to push the propellants out that was compatible with N2O4, that you could make cycles with. We could use bellers, metal bellers, but they weren't very reliable. They were extremely heavy, and so we had to come up with a better system than that. And then we kind of got to looking into putting in screens in the system, and that was really a hard sell. I mean, I spent lots of time with Aaron. I was convinced that system would work, because if you look at an automobile gas tank, every fuel tank on every automobile has got a sock in it. That sock is about an inch and a half in diameter, and it will suck every drop of fuel out of that gas tank. They put it in a little sump in there, and it will just draw that tank dry before it'll break down and let air go through it. So I was convinced that we could build one of those systems and make it work. But you look at an automobile, you know, it goes over rough roads, it bounces, you got G-fields, you got all kinds of forces on that thing, and yet it works very good. The problem we had in trying to sell that concept to the program, though, was how do you prove it? The only technique we had to prove it was through analysis. And you're trying to prove that something like that will work purely from analysis and qualified by analysis was a hard sell. We later on in the program came up with techniques that where we could wrap tape around most of the screens in there so that we close up most of the area, and so we draw propellant in very small areas with air spaces on top and prove that you could get down to a certain delta P and across it before it would break down to qualify our analysis. We still wasn't satisfied with that, so we made up a system with a glass tank. We put it on our Vomit Comet and flew it. And that was the only time I ever rode that thing, and we'd made one more time, it would have been all over for me. But you get up 38,000 feet and you make a dive on that thing, and you can maintain 0 G in it through that 30-second or 38-second period of time. And by expelling the right amount and having it at the right levels, we could prove that it would work. And it has worked very, very good on all of the flights.
Put your crystal ball, look at your crystal ball. In the future design of spacecraft, what is going to be the difference in the RCS system? Because every system is going to have some kind of reaction control system. What do you think they're going to go with in the future system?
I really believe that we ought to go with either methane and LOX or alcohol and LOX. I think it's a much cleaner system. You know, we developed that little piezoelectric igniter for the shuttle program. We never used it after we went away from those systems. But you buy these little batch torches now that you push a button and pull a trigger on it, and they light off most of the time. Although the last one I got, that's all right, just leave it off. Last one I got didn't light too good, but we have good, reliable ignition systems now, and I think that you can design a system now that has the reliability that you need for a space system. Otherwise, you know, we've done nothing in this country since the shuttle program on developing.
Most of it is very important too, and we got to give you the right.
The things you got to remember is that you got to remember the thermal characteristics is very, very different in a vacuum than it is. Than it is on Earth. It is very different in the absence of gravity. You wouldn't think gravity would make any difference in it, but it does. You got some fluid in the tank. You know, you put some heat on the bottom of the tank. Where does heat go? It goes to the top of the tank. Top of the tank is always the hottest part when you got a liquid in 1 G. You put it in 0 G, you put heat on the bottom of the tank, a bubble forms down there, it pushes the liquid away from it, and nothing comes out of the tank. Let me have some questions.
Slightly confused on the fuel that the systems uses. Both the RCS and the homes use hydrazine or hypergolic, or what is it?
Well,
I'm confused on what.
okay, hydrazine is N2H4. We use that as a monopropellant. A bipropellant, storable.
Not explain with the monopropellant system. You normally run it over a catalytic bed, right?
A monopropellant, yes, and a monopropellant. There's two monopropellants out there that work very good. One is peroxide, hydrogen peroxide, and if you can get it above 90%, it gets a little more stable. And the other one is hydrazine. Both of those you run through a cat bed, a catalyst. When it hits a catalyst, you get the reaction out of it, and it breaks down. Hydrogen peroxide breaks down to steam and hydrogen, or oxygen, and hydrazine breaks down to hydrogen and ammonia, NH3. but both of those give you hot gases then for propulsion. You mix that with an acid, and you get combustion. And we used Aerozine 50. I mentioned that. Aerozine 50 was 50% hydrazine and 50% unsymmetrical dimethyl hydrazine. Monomethyl hydrazine is just that. It's monomethyl hydrazine. It's a lot more stable than is hydrazine. It has a wider freezing boiling point than hydrazine. Hydrazine has a lot of the characteristics of water as far as density, freezing, and boiling. It'll freeze at about the same temperature as water. It'll boil at about the same temperature as water, and it has almost the same density as water. Monomethyl hydrazine has a little bit slightly less density, gives you slightly better performance, but it freezes at like minus 63 degrees or something like that. Monomethyl hydrazine and nitrogen tetroxide. Same thing for the ohms. Now, one of the things we do is we put about 0.4% of nitric oxide in the nitrogen tetroxide to keep the tanks from breaking. We have titanium tanks, and on the Apollo program we got into a very serious problem because our tank started exploding. Turned out with Aerozine 50 or monopropellant hydrazine, we had a little bit of water in there, and that gave off a little bit of free hydrogen, and that free hydrogen, titanium just does not like hydrogen.
Is this where the fracture mechanics really started?
Yes.
How many people take fracture mechanics? Well, fracture mechanics really started from that. That's when we started working with a gentleman called Dr. Tiffany at Boeing.
We worked with the whole world on that problem.
Fracture mechanics. That's how fracture mechanics really got started.
You had you're going to ask something.
Let me
Yeah.
another thing while we're talking about fractures. One of the other problems of dealing with these hypergolic fuels is the freezing problem. Maybe we talk a little bit about that, because when unlike water, when the hydrazine freezes, it shrinks, and so if you imagine that you've got hydrazine liquid in a line under pressure, and now it gets too cold, so it freezes. And now that leaves a little bit of free volume, so you get more liquid that comes in there, and that will freeze until finally the entire line is clogged up with solid hydrazine. Now, when it warms up, it expands, and you crack the line, and now you've got a hypergolic leak, which is really bad news. So, in fact, maintaining thermal control of the ohms and RCS propellant lines becomes a very critical issue, and there's heating coils all over the place, and thermostats, and so, you know, again, you don't just have a propulsion system. In the systems engineering that we've talked about, it affects the thermal, the electrical system, because if all these things are interrelated. If you lose an electrical system so that you can't run the heaters, then you run the risk of losing your propellant system, and so then you have to have redundant heaters and so on, and it gets more and more complicated.
That was a major problem we had on Apollo 13. We didn't have enough power. We had to turn everything off quick and try to get those people to let the temperature go down out of limits was not easy. And I remember sitting down and spending the entire night running out the thermal calculations and back calculating out when we could turn the heaters off, or we could kick the service module off of the vehicle and not freeze the propellant in the RCS on the command module. And then I got really worried. I gave myself 4 degrees above freezing on that system, and I missed it 2 degrees. It got 2 degrees colder than we had planned.
I think you have to say, in summary for the students, that the design of the RCS system was very complicated. And how many RCS thrusters do we have? 40? How many thrusters do we have on the shuttle?
38. 38.
38 primary and 4 vernier.
Yeah.
And so it's a very complicated system in designing it. It had a lot of requirements placed on it. On the other hand, the OHMS engine, as I recall, we have never had a failure on the OHMS engine.
The Holmes engine's been very, very successful. It's a very straightforward program. By getting the combustion close to the injector on the ohms, then we could make the chamber small on the ohms, and by making the chamber very small on the ohms, then you could fuel cool it. You could put cooling channels down the chamber, run the fuel down there, and keep the chamber cool so it wouldn't burn out. Now, we also did the same thing on the RCS, a little bit different. You know, the RCS is a buried installation. You run that engine for 500 seconds or more, as we have to run if we want to use it for deorbit in case the ohms plays out sometimes. That engine has to stay together on these very, very short burns. It also has to stay together on these very, very long burns with fluctuating inlet pressures and fluctuating mixture ratios. We found that if we make a very, very short chamber, and that's why when you look at the RCS, it's a big chamber, it's very short, we could put enough fuel down the walls of that chamber to effectively cool the chamber so that it only go up steady states to a certain safe temperature and still have good performance out of it. So we put a lot of fuel down the walls on it.
If looking in this direction, if this is the injector plate, the holes around the outermost layer, those are all fuel. So
yes.
You basically get a fuel bath coming along that actually comes in contact. And fuel, if you have a fuel-rich mixture, same as in a car, the fuel-rich mixture burns cooler. The thing that you're really afraid of, in fact, you have to deal with a lot of contingencies on this system. You know, what happens if you get a clog in one of your feed lines? The worst situation you can get in is that you get a clog in your fuel inlet line, and that gives you an oxidizer-rich mixture which burns hot, and you can then actually get a melt through, and so you got to shut your engine down in a hurry if that happens.
Yeah, these are very, very small orifices, and a lot of them around the outside of it, and if you get a couple of these orifices plugged, then that becomes a hot spot on the side of the chamber. And we used columbium, which has very poor heat transfer. We used molybdenum on Apollo, which has good heat transfer. But
to return to your point about the possibility of using the RCS as a backup for
yes.
reentry, what prevents one from using a series of relatively short burns, counting upon the mass of the orbiter to smooth out the velocity change? Why do you have to have a single 500-second burn with all the heating that's associated with it?
It's just a matter of before you start to burn, you know, to come back in, how much time you can put in between those and how short. A 1,000-pound thruster for deorbit takes a fairly long burn, and the engine goes to steady state fairly quick, you know, in a matter of 20 seconds. If you make a 20-second RCS engine, it is essentially at the steady state. So you can just continue that out. We ran RCS engines for the shuttle up to an hour and a half on a single barn. Just let them run till that's as large as our propellant tanks were. Otherwise, we run them longer. But to get enough delta V, you have to put in, even though you put it in multiple burns, you still have to have fairly long pulse widths on each one of them, and that impacts guidance very, very bad.
Now let me help with a little orbital mechanics. We talked about this before.
Yeah, I'm correct. I have to borrow this one.
Okay, that one's covered.
I'm just hard on mics. Probably won't be able to understand English. I got safety very, very bad today.
So that's you're in orbit. When you do a burn, you do a retrograde burn, which lowers the other side of your orbit, so that now becomes the perigee. The thing is, from orbital mechanics, the most efficient way to do a burn is to have, like Henry said, an infinite thrust with a zero pulse width. So you do what they call an impulsive burn. But in the real world, that never happens. Now, you know, it's 45 minutes from here to here. It's a 90-minute orbit. Now, when you have 2 ohms engines, typical deorbit burn lasts 2 to 2.5 minutes. So, you know, you're burning over this segment. So, you know, it's pretty close to an impulsive burn. If you lose 1 ohms engine, now you have to double it. So now you're up to a 5-minute burn. But if you lose your 2nd ohms engine and now you have to do an RCS deorbit, now you're getting into a 10, 15-minute burn, and so you're actually really far away from optimum, and the burn gets much less efficient. And so if you have plenty of propellant, yeah, you're fine. But if you're low on propellant, you need to worry about the efficiency of your burn. And so, you know, if you were to do a little bit of a burn and then shut it down to let your engines cool off, and then you try to complete the burn around here, now it's gotten really, really inefficient. And you might run out of propellant.
We spent an enormous amount of time with our orbital mechanics people and our guidance people trying to get the ohms thrust down as low as we could get it, because the lower you can get it, the smaller the hardware, the lighter the weight of the hardware, and the performance is essentially the same. The ISP for a 3,000-pound engine is essentially the same as it is for a 20,000, or maybe even a little bit higher for a 3,000. So we had 5,000-pound thrust in there. We had 4,000-pound thrust in there. I think we finally wound up with 3,500. Been left up to me, I think we could have done it with a 1,500-pound thrust engine, but we compromised. Quite, yes.
Professor Cohen once mentioned that some people suggested putting some RCS thrusters on the edge of the wingtips, but that would be very difficult after the design was finalized.
All of our early configurations that we had the RCS pods out on the wingtips. Made the RCS very efficient. We even had a combination of ohms. I mean, our RCS was the ohms at one time, and we had it all out on wingtips. Didn't make our structures friends too happy at first, because that puts a lot of mass out into the wings, and they didn't like it too much. But after they got looking at it, that turned out that really wasn't much of a driver. It made the RCS very efficient. The thing that kind of changed that is when we put the big payload bay on the inside of the vehicle, and then we had to put a big ohms pod on there, and then to put the RCS pods out on a wingtip of a Delta system out there just didn't weigh out good. It was more efficient from a weight standpoint to put the ohms and RCS together, because we actually have those two interconnected. So if we have to do an ohms burn with the RCS, we can take the propellant out of the ohms tank to feed the RCS. And so it just made a more efficient system to bring it all in. We had another requirement. When we went to the acid-based propellants, we had a requirement that we had to have removable pods. You had to be able to take a pod, the propulsion system, off of the orbiter and take it over to another facility to rework it, because we knew we were going to have a lot of work and rework on those systems, at least early on. Let's see, you had a question right here.
Yeah, to what extent can we change orbits, go to a higher or lower orbit for different part of the mission, or?
That's very limited, but yeah, we do have the capability to go up and down in orbit. I don't know, maybe 50 miles. I don't know. I don't have a good answer. I don't remember that. That's been too long ago.
With a full load, you have a few hundred feet per second. I'd have to go and look up.
You can't make a plane change.
No, plane changes are out, but we certainly have gone from let's see, like 180 nautical mile orbits down to 105 mile. I remember one flight where we did that. To go up, after what you really want to do is, of course, use your main propulsion system to get into the right orbit that you want to go to. Then, if you're going to do a rendezvous, you have to change the height a little bit, but you typically try to get orbit insertion within about 20 nautical miles, so about 40 kilometers of radius of your ultimate intended orbit. But for some special missions, like I was on one mission where we were up at about 180 nautical miles doing various operations, but then the last couple of days they wanted to look at the interaction of the orbiter with the atomic oxygen and nitrogen, which caused this orbiter glow phenomena, which maybe some of you have heard about. But so we had to go down to about 105 nautical miles, which is about as low as you can go and stay in orbit for more than a day or so. And so, yeah, I mean, we that was okay because, that was just, you're doing part of your deorbit burn, but then you stop. What you wouldn't want to do is go to 105-mile orbit and then go up, and then you have to come all the way down again.
I think I'll take one more question.
It's awful easy to to decrease the orbit because you're using part of the energy that you have to use to come back home anyway. When you start trying to go up is when you're adding, but we have a lot of contingency propellant on board. We got contingency propellant in case the main engine shut off early and you have to use the RCS. If you got a docking mission, we've got propellant in there for 3 or 4 attempts at docking and things like that. So there's extra propellant that you can use to give you a little bit boost. You had a question here.
It's talking about the blocked fuel line causing an over temperature and presenting hazard that way. What kind of feedback did the crew have? Something like that was happening. Were there sensors in that system that the computers or physical instruments that?
I don't hear too good, so
yeah. There's the question is what sort of sensors do we have for the operation of the engine? So and I mean I can there's pressure sensors, there's temperature sensors. Again, remember when we were talking earlier, though, sensors don't always tell the truth. Sometimes you can get sensor failures, and so we spend a lot of time practicing, and you work out all the different scenarios. This is what you'll see if you have a real failure. This is what you'll see if you have a sensor failure. You try to get, before you shut down a good working engine, you'd like to confirm the fact that it's really an engine problem, not a sensor problem. On the other hand, you don't want to take a chance that you're going to get into a oxidizer-rich situation and blow up your engine. So you practice, and after a while you get pretty good at diagnosing the problems fairly quickly.
So that wasn't feeding the computer, that was feeding
the computer doesn't normally shut down the OMS engine on its own.
The computer won't shut down any of the propulsion systems on its own.
Well, it shut down the main propulsion.
The main engine, yeah. But none of these will it shut down on its own. Somebody's got to take some action to shut it down. We get an awful lot of data on the ground too that you don't have in the cockpit, that you can look at different instruments and back up things and try to understand whether it's a sensor failure or. Okay.
Any other questions on OMS RCS?
What during entry when you're coming down using the RCS for like trajectory guidance before your aero surfaces are usable, how much propellant would you typically use? Is it like a certain percentage that would be average?
That's a pretty low percentage, and I don't recall. That's been a long time now, and I don't recall the numbers. But I would say it's less than 10% of the propellant that we. What did you say?
Yeah, about
okay.
10%.
Okay. Well, at least that ought to be a pretty good number. It's not a lot of propellant to come back in on it. The vehicle is a fairly stable vehicle. Now, on Columbia, they I guess they either run out of propellant or just about run out of propellant on it, trying to hold it when the RCS was doing all it could to try to hold that vehicle on course after it started picking up drag on one side.
And we actually did have procedures in place for what we called a no RCS entry. If you had run out of propellant entirely, don't know if it would have worked, but we there were certain you tried to get it into as stable an aerodynamic situation as possible and just hold it there. So never had to actually do it.
I'll take one.
Any more OHMS RCS questions? Otherwise, why don't we take a little break and then we'll come back for APU hydraulics. 2-minute break. Okay.
Thank you all. Appreciate it.
You're not finished. Okay. Time to go.
APU and hydraulics. And I guess I need to point out some acronyms. Calling the APU an APU was the biggest mistake we ever made. That gave me more grief than any other system that I had to deal with, was the acronym. APU stands for Auxiliary Power Unit. And the Aerospace Safety Advisory Committee,
I'll tell you, Henry, my kids, when I was growing up, used to think it was a three-letter bad word. I mean, they thought APU was a bad word. Every time I got a call, there was something wrong with it.
if we would have called it Primary Power Unit, then we would have had a lot less grief in trying to vend it to the outside world. APU hydraulics, like the OHMS and RCS, all of our first activity was directed toward keeping the operational cost down low, keeping the maintenance cost down low, and we looked at those kinds of systems that gave you clean propellants, easy propellants to deal with, and you didn't have to worry about the strong bases and strong acids to work with. Later on, as time went on, we got more into looking at what we could do cheap from a development standpoint and let the operational cost float, because it's obvious that the money was not going to be there to put into a big development program. The control of the vehicle in the atmosphere was a major activity to try to find out what you could get by with versus what you would like to have. Now, you know, you try to move these huge barn doors fast and a whole lot. There's huge forces on those things. It takes lots and lots of power to move them, and move them quick. And our aero people and our guidance people, they would like to have, like we was talking a while ago, an instantaneous impulse into that vehicle. When it starts to drift a little bit and they want to move it some other way, they like to put an impulse in there and just kick it right back where it's supposed to be instantly. But that becomes impractical when you look at these kind of systems. We started out with dual tandem actuators. Now, dual tandem actuators is something that kind of met our fail-op, fail-safe criteria. In other words, you had two pistons in one actuator driven by two different hydraulic systems, and you would move them together. When you start looking at all of the failure modes associated with dual tandem actuators, even though it meets the fail-op, fail-safe criteria and it makes the safety people happy and the people that's looking at the buzzwords, it actually was making the system less safe.
Is that because you have single passages that could dump all the hydraulic fluid?
No, that what happened in a dual tandem actuator, in order to get them to work good, if you busted an actuator, then that became a big sponge. You didn't have any way to take that space out. So trying to have that actuator work when the other half went out made it very, very difficult from a design standpoint to come up with a system that you could lock it in place. And we even had designs where if one hydraulic system failed, that shaft would actually lock itself. With the absence of pressure, it would lock itself. Well, that becomes a failure in itself, because if that mechanism fails, then you've got a locked actuator. And one thing you can't stand on an airplane is for an actuator not to move. We were finally able to convince the people, and Aaron was having lots and lots of problems about that time, because all of the weight was in the back end of the vehicle. Those dual tandem actuators were extremely heavy, and the back end of the vehicle was getting too heavy. So we actually went to a single actuator, and we put switching valves in there where we could switch any one of the 4 APU systems into that actuator. And we had 4 APUs at that time. Weight was still a problem, so we were able to convince the community that we could live with 3 APUs and have 1 APU fail and come home in a normal mode with 2, and if you had 2 failures, you could still land the vehicle with one actuator. You lost a whole bunch of systems, but you could still land it with one APU. And we almost did that one time, because if someone would have told me that we would ever have 2 failures of the same type on the same flight of the nature that we had, I would have never believed it. But we came home on one flight with 2 APUs burning. We had a fire in both of the APUs. And the reason for that, after the fact again, is very, very simple. We went through a very good qual program. We did everything that we knew to do on those things, only to find out that we had not planned on landing the vehicle in California and piggybacking it back down to the Cape over and over again. What happens when you do that is that you land the vehicle, there's a little bit of residual APU, hydrazine in those tubes between the valves and the injector. You go back up into a vacuum or low pressure, all of the air goes out of the system, and then we come and land in Florida. It's always humid in Florida, there's a lot of moisture there, and as that moist air started feeding back in the engine, it went up past the cat bed and got in those tubes between the valve and the injector, and set up a very, very corrosive environment of residual hydrazine and water. And they gave off free hydrogen, and you had hydrogen or intergranular corrosion in those tubes, and we had 2 of them to break on the same flight. But it worked. We spent an awful lot of time looking at power sources to power the hydraulic systems. And we even looked at going with all electrical systems. You know, the DOD had some very good fuel cells out there that had a lot of promise. They put out an awful lot of power at that time. The shuttle fuel cells. You know, let me just digress a little bit and talk about shuttle fuel cells. I don't think anybody can cover that. You know, on Gemini, fuel cells never did work. We always came back with half voltage or partial voltage, and most of the fuel cells out. On Apollo, it only took 14 PhDs and 14 PhDs to start them and shut them down. And then you couldn't start them again. On the space shuttle, those fuel cells is just a very, very good battery with the chemical stored external to the battery. They would make an outstanding DC welder. I mean, you could put electrodes in that thing and put electrical rod in there and strike an arc and weld with them and break the arc, strike an arc and weld and break the arc, and they just do it repeated. You can throw a switch, they're on, you throw a switch, they're off, and so they're very, very simple. I really, really wanted us to go with an all-electrical system, using electrical motors and power hinges and power electromechanical actuators to drive the systems, because I was absolutely convinced that one of these days we're going to have a leak in the hydraulic system, and when we have a leak in the hydraulic system, we're going to have a fire.
So it's very difficult. You know your car. It's very difficult to keep.
You always have hydraulic. All airplanes have hydraulic leaks. Now you don't have to worry too much about hydraulic leaks on an airplane, because you seldom ever get in enough pressure where you seldom ever have to worry about a fire. We went from 5606 hydraulic full fluid to 282 hydraulic fluid simply because it was advertised as being more flame resistant. It's really not more flame resistant. The 282 hydraulic fluid has a much, much lower vapor pressure than does 5606. And the way that they test it is they've got a Bunsen burner out here. They take a pipe cleaner and dip it in the fluid, clamp it in this device that rotates past that Bunsen burner, and they count the number of times it'll go across it before the fire starts. Well, with 5606, it'll usually start on a third burn. With 282, it takes 10, 11, or 12 passes before it'll ignite and start burning, simply because it has a lower vapor pressure, and you cannot burn any liquid in liquid stage. You have to get it warm enough so that it'll gasify, and then you have to heat it enough in the gas phase to get it up to the combustion temperature, or put a spark in it after it's in the gas phase, but it won't ignite as a liquid. Well, with 5606, if you have a leak in the hydraulic system going uphill, you probably don't have to worry about it coming home, because it's gone. It all boils off and it's gone. With 282, all it does is soak out into the structure and in the insulation and all over the place, and then when you come back home, if it gets in a hot spot and you start heating it up, it forms gas, and you're going to get an explosion in the back of the vehicle.
So we made the wrong decision.
So that was a bad decision there, and we went in a bad direction, but it gave everybody a warm feeling. We would have went with electromechanical system, but by that time we had a lot of hydraulic people working on the program, and we would lay those people all off, and we had to go hire a whole bunch of electromechanical people, and a lot of people was concerned about the immaturity of those systems, and again it boiled down to development costs.
Do we really have the energy source that could handle that?
Oh, I'm convinced that we could have put 6 or 8 of those fuel cells that we've got on there right now on there, and we could have handled it. You know, broke it down, and the fuel cells that the DOD had under development at that time was very, very good fuel cells. So
maybe if you were doing the system.
If I was upgrading the shuttle today, that's one of the things that I absolutely would go to. I would go to something to get rid of the hydraulic fluid. It creates a lot of other kinds of problems that you have to deal with.
But actually, before the decision was made that the shuttle was going to be retired in 5 years, NASA was working on upgrades if we were going to fly the shuttle for another 20 or 25 years. And one of the upgrades, which actually got to a fairly advanced stage in the design, was just what you were saying, was get rid of the APU hydraulics, use the latest technology now available for electromechanical actuators. But the problem, I don't know the details of it, but the cost just kept going up and up and up, and by the time it went up above about $300 million, they just said, you know, we can't afford to do this. And
Yeah, the problem we always had in trying to upgrade the propulsion, you know, we could have went to alcohol lock space RCS gnomes on it. We could have upgraded to an electromechanical system, but it seemed to me like that the displays and those kinds of upgrades took a lot of computers. You know, those systems took a lot of priority in where the monies went in trying to upgrade the orbiter. Go ahead and throw the next slide up there if you can do it real handy. Oh, wait.
We did go from 4 to 3 systems.
Wait a minute. You already got it up here. I wasn't watching. We did go from 4 APUs to 3 APUs, and still having the ability to land the vehicle with one APU. We looked at hydrogen-oxygen APUs. We looked at bipropellant APUs. We looked at monopropellant APUs. We looked at pulse modulated versus pressure modulated. If you don't know what I mean by that, pulse modulated is when you have a valve that goes open and closed and you get steady state pressure in your gas generator while it's on. Pressure modulated, you have a throttle valve where you throttle the flow down going to the gas generator to give you just the power that you need for the load that you're trying to pull at the time. And that was the easiest system to come up with, simply because we didn't know at the time if we could build a valve that was capable of millions and millions of cycles and not leak. But the problem with the pressure modulated system was that most of the time you're operating at very, very low power levels. Just the power just peaks up every once in a while to high power levels. Well, when you're running very low pressures in a gas turbine, the turbine becomes less efficient. And the less efficient the turbine becomes, the more propellant you have to burn, and again, the weight goes up. So we kind of bit the bullet on that and went to a pressure modulated system where we varied the on time. And the valve development was very successful. We had very little trouble getting a valve that would work except for contamination. We always had a little contamination. We had a lot of problems down the Cape with the early valves leaking. We finally got good filters, put good filters in the system, and that eliminated that. We did, yes?
Was the reason to go from 4 to 3 APUs just a weight issue?
It's again a weight issue. All of that weight was in the back of the vehicle, and the back of the vehicle was always too heavy. And every time we could take a pound out of the back of the vehicle, we could take a pound of ballast out of the front of the vehicle. So there's 2 pounds you didn't have to carry. So it's strictly weight.
I'm sorry. The APUs are turbines. I mean, you're combusting something.
The APUs, what we settled on was going with a monopropellant hydrazine. Feed that through a catalyst bed, and then through a turbine. We looked at dual stage, triple stage turbines. We finally wound up with a single stage turbine running at about 38 to 45,000, I don't remember the exact number now, RPM.
10-inch diameter.
Yes, about 10 inches in diameter. It's a re-entry wheel. The gas went in and then made a pass and went back through. So we got maybe 5–10% more power out of it the second time through, a little bit more power out of it the second time through. When we contracted for the APU, the contractor did not have altitude facilities. And so they proposed that we did not need to test the APU in a vacuum because that was all structure, and all they had to do was pull a vacuum on the exhaust and they could get the performance out of that. So we did not have it in our qual program to test the APU in a vacuum. Fortunately, Dr. Coyne gave us enough money to buy an APU offline of the shuttle program. We brought it down to the JSC, we put it in our vacuum facilities there, and we programmed the vacuum facility to go down in pressure like the orbiter was going up in altitude, and we ran the ascent profile and shut the APU off, just like we would on the first flight, and 5 minutes after we shut it off, it exploded. It detonated. I mean, talking about things coming unglued, everything came unglued. Aaron came unglued. We got another APU, we brought it down there, we brought all of the contractor people down, everybody down there, we repeated the test. It exploded again. By that time, we discovered what the problem was. We have a requirement in the program that you can only have hot surfaces up to about 500 degrees, or I don't remember the exact temperature, but some temperature like 500 degrees. If it's higher than that, you have to shield it. So the gas generator is obviously running over 500 degrees, probably up around 800, 900 degrees. So we put a heat shield around it, covered that whole thing up, and we had about a half-inch standoff in the insulation on that thing. When you run it in 1 atmosphere and you shut it off, it acts like a chimney. The air heats up between the insulation and the hot surface. It goes out the top, it draws cold air in. It goes out the top, it draws more cold air in, so it cools it off. So the heat never did soak out into the valves and get the valves too hot. When you put it in a vacuum, there's no place for that heat to go. And so all of that heat that was in the gas generator and all of the catalyst and all of that soaked back out through the structure and through the tubes back up to the valves and got the valves up to the temperature at which hydrazine will detonate. And it did. It's so simple, it's so easy to understand after you know about it, but to think about it. I remember sitting around there one night until 8, 9 o'clock with all of my troops discussing the pros and cons of an altitude facility. Do we have to have it? Do we have to direct the contractor to put one in? And we could not come up with a good reason to put an altitude test in the program, so we didn't put it in there. Fortunately, we had a just like on ohms with the helium bottle falling out, we had a backup because some of the people wasn't confident in flying the vehicle without that test. And we found something that we didn't expect.
The message that Henry's giving you on testing is the same message that J.R. Thompson gave you on testing on the main engine. And in contrast, we didn't really do that type of testing on the solid rocket booster, the fare we had, and on the foam. And that's the difference. We really tested. When we saw a problem, we tested it. And, you know, fortunately, we came up very fortunately that we did do it.
Another thing with the development of the APU, you know, we flew those things on airplanes all the time in case they lost main engine, or fighter aircraft, and some of the other airplanes, including a supersonic plane that we had. It had APUs in there in case they lost engine power to provide hydraulics to be able to land the vehicle. And that's where I got a lot of the flack, because the Aerospace Safety Committee told me that those systems never did work because they're called auxiliary power units. They never worked when you needed them. But they had those systems, and they were good systems. But when we try to use that same kind of design on the shuttle, the oil wouldn't go back to the sump. In the absence of gravity, you know, you sling it out and it just coats the walls. It won't go on an automobile, you know, you put an oil pan down the bottom, you put a pump right in the bottom, and put a little filter in there, pump the oil out and pump it through the engine, use it over and over and over. But when you have no bottom, you have no place for that oil to go. So we had to come up with a technique of where we could use the gears as oil pumps. And we came up with very, very close tolerances between the gear and the case, and let the gear sling the oil out or pump the oil out into a cavity and pipe it off to where we had a sump to where we could pick the oil up with an oil pump and pump it back through the system. And you know, we had some problems with some hydrazine getting in there and gelling at one time, and Fram came out with this deal where you can pay me now, you can pay me later kind of thing, because they accused us of not changing the oil filter. Hydraulics was mostly off the shelf at the time. The pump and that stuff. We did go to titanium propellant lines, or hydraulic lines. We did go to developed a special fitting to put titanium lines together that turned out to be very, very good. We did have to add a water boiler to cool the hydraulic fluid, because on airplanes, just put a little radiator in there and use the atmosphere to cool it, but that didn't work in space, so we had to put a water boiler. The first one they came up with was a bucket, and they had a coil of tubes in that bucket with a pipe that went out with some baffles in there to keep the liquid from going out. But there again, they did not understand the absence of gravity. When in 0 G and you put heat in that water, it just pushes the water out away from the tube, and all the water go out the exhaust pipe, and you'd have nothing but gas in the tank. So we had to change that design and go into what we call a water spray boiler to pulse the water in there as a spray. Is more efficient, but complicated that system very much.
And it used to freeze up.
Still does.
Yeah.
Still does.
Yeah.
It's very, very difficult to handle water in a vacuum. You know, getting back to the RCS one moment, you know, first rain we had down there at the Cape, the RCS just filled up with water. And they wanted to launch a system, and assuming that the water would boil out when they started going uphill. But no, what happens, you put water in a vacuum, about 60% of it will go to a gas, and 30% of it will freeze. When it freezes, then it's a solid. You can't get it out. It just has to sublime, which takes weeks and months. Now, trying to get a water boiler, we had valves in there that would supposed to open and close when the pressure built up. Well, when you get past that valve, when that valve would open up, that steam would instantly freeze on the outside, and it keeps growing back. Finally, the valve would be stopped up, and you'd have to build the pressure up way high, and it'd blow the ice out. The pressure would come back down. It started working again, but so we went to an orifice. Now, try and size that orifice at the right size where it maintains a little pressure in there, and you got a variable load on the system, and you're putting variable energy into it. That's difficult to design that too. So the water boiler still freezes. We still have a freezing problem on it. It's not an easy solution to it. Questions?
You lose that water? Does that escape into
the water? Yeah, we just dump it overboard. It goes through. We got a whole bunch of tubes going through this boiler, and we spray the water in a spray, and it makes one pass through those tubes, and then it goes out the exhaust. We didn't try to, you know, if you wanted to come up with some kind of regenerative system where you would use the water over and over and over, then you got to go through some kind of system to cool the water, or you have to carry too much water aboard. Well, if you want to cool the water, the only way you really got to cool it is by using more water or supplementing some of that water. You can't just, in a vacuum, you can't just put it out on a surface someplace and you know, I guess the temperature varies maybe.
Henry, could you say a word about the flight control hydraulics lab, the test we ran in
Fickle?
Yeah, with the hydraulic systems?
The hydraulic system was probably one of the most thoroughly tested systems that we had as far as mechanical systems was concerned. We built a whole hydraulic system integrated with the avionics, and we had it designed so you could put loads on it, react the loads. you could program in what you thought was typical emissions, where you could vary everything. The only difference is, instead of driving the hydraulic pumps with APUs, we drove the hydraulic pumps with electric motors, because we had ground-based electric motors to drive them. The very first test, and one of the things we ground ruled out, was use of flex hoses, bellows, simply because they, at that time, were notorious for fatiguing and breaking and not working very good. So we put trombone tubes in, take a long tube and bring it back this way and tie it in. And now as the actuator moved, it could move, and you had enough spring or enough give in those tubes. On the very first time they fired that thing up, standing up there in the control room looking at it, and those trombone tubes just vanished. They'd be there, and then all at once you wouldn't see them. And I mean, you couldn't see them. You're standing up there in the control room looking, there's no tubes in there. They were shaking so bad that you couldn't see them. So we went through a big effort to figure out ways to damp those things and isolate them so that they didn't vibrate.
We also had a hydraulic leak where we nibbled some O-rings and lost.
Oh, we had a major failure. We went to it was a hard sell to convince the people to go to a single actuator, from dual tandem to single actuator. Well, no more than we got our first single actuator built, then the initial design had too much slack in a tube that went from one side to the other side, because you had to have an expansion joint in there, and we had no ring in there. And they had too much slack in there, and it blew one of the O-rings out. Well, of course, when you blew an O-ring out, you lost all the hydraulics, not only from that system, but all three systems, because when it was downstream of the switching valves, and when one system ran out of fluid, it'd switch over to the other one, it'd run out of fluid. And had we not had a very, very strong guy in the program office at that time that never gave up on anything, that would have probably finished us off as far as single actuators are concerned. But we were able to convince the program that it would tighten the tolerance up on it, paid very close attention to the tolerance on it, that could not happen, and it has not happened again. Now the question. Yes?
You talked a little bit before about maybe substituting an electromechanical system for hydraulic. Would there be any other changes you'd make in the design if you had to go back and do it again?
If I had to do it again, I definitely would go with electromechanical systems. Now, that takes on many varieties. You could have small electric motors driving a hydraulic system right at the unit, like you put an electric motor on an actuator. And that electric motor drive a small hydraulic pump that would move the actuator if you did not have confidence in worm gears and screw jacks and those kind of things to provide the mechanical force, power hinges and things like that. But there's absolutely no question in my mind that one of the safest things you could do for the Arbiter right now would be to replace the hydraulic system, the APUs in the hydraulic system, with an electrical system. We have the motor technology. We have I think the gear and the ball screw technology to be able to do that. I think we could do it cheap.
I think it would really change it would also change the operational cost.
It would reduce the operational cost immensely. It would move the CG further forward on the vehicle, so you probably could take out a little bit more of the ballast that we usually fly in the front end. I guess we're still flying it. We always did.
I've got another question.
Yeah.
I was wondering, you talked earlier, and you had it on the slide, but you didn't really talk about it, how you were shifting weight between budgets, when it came to like the controls people versus the hydraulics people and the APUs. I was wondering, kind of, you just expand on that of how in an actual development program it goes back and forth. I mean, is it Is it usually come down from high, you're going to do this and you're going to do that, or is it usually they let you kind of work it out between the two groups, or what?
The control people have no weight budget.
Right.
I mean, their budget is the electrons that flow back and forth and the requirements. So what they do is they start out with a requirement that they would like to have. And it's usually 2, 3, 4 times what they absolutely have to have. And then you have to sit down and start negotiating with them and explaining to them what it's costing. And often it gets down to the fact that the vehicle won't fly. I mean, it just flat won't fly. And when they're convinced then that it can't fly, then they're willing to concede that they can get by with a little more. And so it still won't fly, so they can get by with a little bit more. And that's kind of the way you get it down.
Normally what you have, start off with project, you have what they call work breakdown structure. Are you familiar with the term work breakdown structure? So that's what you do, is you have a work breakdown structure, and you parcel that work breakdown structure out to your subsystem managers. Now, there was an issue in the shuttle and the Apollo program, since I was the project manager. You give the subsystem managers the requirements and the authority technically, but you do not give them the authority. You tell them what their constraint is for dollars. You give them the weight. You give them the weight bogies or the weight requirements, the functional requirements, performance requirements, the schedule requirements, but you keep the dollars. Now that's been a very long argument. Do you allow the subsystem managers to actually have control over the dollars? We decided not to. That was a very, very big argument of whether you should let the other people have the dollars. I kept the dollars. So they had to come to me if they wanted to make a big change outside their work breakdown structure. And because I had the problem of trading off the dollars between the propulsion system and the structure system, or the aerodynamic system. And you can argue that was the right or wrong thing to do, but that's how we did it. And I'm not sure aircraft companies like Boeing now or Lockheed Martin, how they do it, but they all start off with a work breakdown structure of some type. Yes?
At that stage, do you also give them target weights?
You give them target weights also, yeah.
Based on previous aircraft design?
Yeah, you give them target weights and negotiated target weights and negotiated schedules, and they develop the performance.
You basically get your target weights from the preliminary designs that you've done to look at the concept that you're looking at to make sure that it's feasible. And when it looks like it's a feasible design, then you break up the weights and you give all of the subsystem people their target weights to stay within, of which almost immediately the weights start growing.
Well, that's right. When you're a project manager like I was, it's career limiting. First thing is your weight starts to go up. The next thing is you start to have schedule slips because your technology problems, you're finding technology problems, and then the cost starts to go up. So you're really sort of you come to with a lot of career limiting problems in project management. So, but you have to have good people working for you. I think, Henry, another interesting thing you might talk about is they've seen Bass Red talk about the aerodynamics. They're going to have Phil Hattis talk about the guidance, navigation, control. You might give them your perspective with a hydraulic system of tying those systems together. You mentioned it a little bit, but it's probably a little bit more. It's probably a little bit harder than you think. And putting the requirements on the hydraulic system.
I probably spent more time, personal time, dealing with the avionics people, the guidance people, and the aero people than I did working with the subsystem designs early on. Just trying to get some reasonableness in the requirements. Trying to get the size of the OMS engines down, trying to get the size of the RCS down, trying to get the pulse width a little bit wider. On the hydraulics, that was a major issue because those were really big weight items. On the OMS and RCS, it was not a big weight impact. It was a performance impact of how much propellant you had to carry on board. But on the hydraulics, on the design of that system, that was how fast you had to move one of those flaps on that thing was a big issue. And I spent lots of time going over and looking at their data, looking at what they were coming up with, looking at their what ifs, trying to get their what ifs. That's what drives the systems. Is what if this happens or what if that happens.
The problem I remember we had is the gimbal rate of the main engines. The requirement they put on the gimbal rate.
That was a compounded problem too, because you were kind of dealing between centers. But yeah, the gimbal weight and the need for a gimbal system on the solid rocket motors. You know, if I had my day in court, we would take the gimbal system off of the solid rocket boosters, and we would fix those. That would save 6 or 7 or 8 tons of weight back there. If you take that system out, it would make the solid rocket boosters much more reliable, because they got those great big old boots in there and those big springs. They horse those things back and forth with huge actuators on them. And the only reason we could not eliminate the gimbal system on the SRBs is that we had one SRB that burned out with the max burn time, and the other one on the other side burned out with minimum burn time, and we lost the top engine on the SSME on the same flight. Now, you know, the probability of that happening is once in a billion, but yet that is what drives the requirement for the having gimbal system. Oh, we'd have to gimbal the main engines another 2 degrees to make that work. But that is what drove the design. That requirement drove the design that we have on the solid rocket motors. So, if I can leave you with one message, is understand your requirements extremely well and understand the impact that requirement is having on your system and on the flyability of the vehicle. Give me another one.
Well, while they're thinking, I'll give you one. I told you that Henry had a lot of innovative design. Now, talk a little bit more about the RCS. I thought you were going to mention that before when they got water and how you solved that problem. This is Henry Pohl's solution to a very complex problem on the RCS system. On the pad.
When we got the RCS engines filled up with water, we needed to come up with a design to keep the water out of the engines in case of rain, because it always rains at the Cape. So that requirement fell on the contractor to design a system to keep water from getting in the RCS engines. They came up with a plug that went in the throat with another big seal to go around those big scarf nozzles out there with an O-ring on that. And that was all tied together with cables, and they stuck a big pole upside the vehicle. And just before liftoff, they were going to pop that pole over and jerk all of that stuff out, and they were going to jerk it out fast enough so that those big things would not fall down and hit the tile and knock all the tile off. Well, that looked kind of complex and complicated for me. So I went down to, we had a grocery store across the street down there then by the name of Weingarten's, and I went down to Weingarten's and I got a roll of what wrapping paper that you use to wrap meats in, that's got wax on one side and paper on the other side. I called it butcher paper, but butcher paper is actually a little bit different. This is actually free. If you go down and buy some, it's freezer paper. But I bought a roll of that, and I got it back up into the meeting by the time it was over, and I said, this is the way to fix it, and then started tearing off sheets out and passing it around to the managers look at. We're going to glue that on the surface with the wax side out and glue it on with RTV. And then when you lift it off, you know, it would come off. It was light. It wouldn't hurt the tile. If it impacted anything, it wasn't going to hurt anything. If it didn't come off, when you fired the RCS, you blow it off or burn it off. And that's what we did. And we flew that on all of the well, you know, there's...
It sounds funny, but it's true. You look at the orbiter sitting on the pad, and all the RCS jets are covered up with paper.
But after I left, they changed that. They changed from butcher paper to a special paper developed special for that purpose. It's made out of Teflon. So that is.
You got to tell them one more story about the SSME on the launch pad and the hydrogen. This was JR's period.
When we did the first firing on the pad, just a test firing on the pad on the launch pad to make sure that everything worked right, we blew the back end out of the shuttle. When those main engines light off, each one of those engines dump out about 125 pounds of hydrogen before it ignites. That hydrogen is cold. It's fairly dense in liquid form. It's 4.5 pounds per cubic foot or something. By that time, it's a little bit lighter. It goes down in the flame pit, mixes with a lot of air in there, and then the flame hits it, it detonates, and it blew the back end out of the vehicle. So we needed a quick fix because we had to launch that thing 3-4 days. I looked at the problem. I said, we'll just put Roman candles under it. You put a bunch of Roman candles under there that firing those balls out across there, and as the hydrogen comes out, that'll ignite the hydrogen, it'll burn, it won't accumulate down the pit. And that's what we did. Those sparklers you see coming on before the main engines light off, that's my Roman candles.
As long as we're talking about blowing the back end of the orbiter out, maybe you talk about the pressure wave as well.
The pressure wave that came back?
Yeah, and the water suppression.
We had another problem. It was more of an acoustical problem from the pressure waves coming back up under the orbiter, and we needed some kind of solution to do that. And back while I was in Huntsville as a test engineer in the test lab there in Huntsville, we blew the windows out 7 miles away when we started firing the Saturn V vehicle. So we spent a lot of time on water suppression techniques to, sound suppression techniques to reduce the pressure effect. And one of the things we came up with, we found water was very good at damping out. So when we had that problem down at the Cape, what we did is put those sausages, the hammocks across down there, and fill them with water to damp out the pressure wave that came back up to the back of the vehicle. So that's another one of them.
Essentially like big water balloons.
We call them sausage. You know, it's just a fabric across the bottom, filled it up with water, strong enough to hold the water up, and then that damped the sound waves, the shock waves that came back up to the vehicle. Again, just remember that it's not natural for earthbound humans to think in terms of the absence of gravity and the absence of pressure. I cannot stress that too much. You take a pot of water and you put it on a stove, it gets hot on top. You put it on a stove on 0G, it don't get hot on top, it just pushes all the water out. Heat transfer, you don't realize how much heat is transferred out through the atmosphere. You have no atmosphere, you don't get any of the heat transfer out. The other thing to remember is that there's absolutely no substitute for a very good, very well thought out test program. It is not easy to test in the absence of gravity. It is not easy to test in the absence of pressure when you're reducing large quantities of gas or chemicals, but that is very, very important, and that is the one thing that really separates a space program from anything that we do here on Earth, is that you have no atmosphere and you have no gravity to help you in your design. Yet all of our thought process is based on having gravity and having an atmosphere.
In some of the designs of various experiments that I've worked with on Spacelab flights and other flights, numerous failures, and over half of the equipment that failed, this is stuff generally that we use inside the shuttle, it was because of thermal problems, that they would overheat just because people didn't get the calculations right. You have no convection, and getting the thermal design to work is just really difficult.
Convection is one of the major problems that's overlooked, because when you put heat in one place on the ground, it goes up. You take gravity away, it will not go up, and that changes the whole complex, the thermal matrix.
Well, and then, you know, Henry talked a little bit about the screen system that was developed for the OHMS and RCS tanks, but, you know, I just to make sure that you appreciate the complexity of this, you know, you get you've probably seen pictures of astronauts playing with food and liquids. You blow these big, you know, liquid bubbles and they just sort of float there. Well, you know, the liquid does the same thing inside a fuel tank. And when you push the button to you want your engine to turn on, you know, how do you get the fuel to flow into the engine? And as Henry said, in the old days, you had a kind of a diaphragm. Everything it was in a like a little balloon, and you would pressurize the outside of the balloon, and that would force the fuel out. But that balloon would get eaten away. I mean, remember that was a system that was only used for one flight. Now we've got a system that has to be reusable, and if you didn't want to replace those diaphragms or balloons every flight, you needed something that was a different system. And that's where they came up with the idea of the screens, which would have surface tension, so enough of the propellant would stick to the screen, and then you would get the helium on the other side that would push it out of the screen. And with the OHMS, of course, once you got the system started, then of course you're producing an acceleration, and it's always in the same direction. So that the OHMS tanks are designed so that they only have to feed enough propellant through the screening system to get the engine started, and then everything is, I won't call it gravity fed, but it's fed by the acceleration. It's about when both engines are burning, it's about 1/10 of a G. But the RCS, that can push you any direction, you know, and so you have to have a system which will continuously feed no matter which direction your acceleration vector is. It's a really complex and clever system.
And the design is based strictly on surface tension.
Why are there so many RCS engines? For example, on the nose, there are what, 16? What? Yeah. Is that for redundancy or?
Part of it's for redundancy. Part of it's make sure that you've got one to cover every direction. We got 3. I guess we got 6 going down in front. Now, we need 2 of those for certain maneuvers. So you can lose 4 of them. And we got, 4 going out. You can lose 1 on either side.
And remember, you need a coupled pair. You would like to be able to do a pure rotation. If you just fire one engine in the aft, you're going to get a rotation, but you'll also get a translation. So you need coupled pairs. And then for redundancy, we have 3 sets. So if you add up the x-axis, the y-axis, the z-axis, so you got to be able to translate in 3 axes. You've got to be able to rotate about 3 axes, and then you need dual redundancy for each of those axes. You add it up and you end up with 38 primary jets. And then on top of that, those are 850-pound jets. They use a lot of propellant. When you're in orbit generally, and all you worry about is your attitude, and you're not doing a propulsive burn for rendezvous or everything, we shut down the primary RCS system, and we just use 6 little 25-pound vernier thrusters, all of which are pointed down. So you do get, when you use those for attitude control, they do give you a little bit of propulsive impulse as well, but it's a small enough thrust that it doesn't change your orbit by very much.
let me tell you another story about the absence of about the expulsion devices on the shuttle. Back in my young days, I grew up in the country, and we had a Ford tractor. Ford tractor had a screen in the fuel tank, and it stood up about that tall, and they had a little standpipe in there, and the valve was such that when you got down, you could set the valve one way, and it'd leave about a gallon of fuel in the tank. You turn it the other way then, and it would use that gallon of fuel out, kind of like a gas gauge on a Volkswagen, on the earlier Volkswagen. Well, what happened is that I had that out one day, and it had a hole, 1/10 of an inch diameter hole punched in that screen, about halfway up on the screen. I said, well, that screen's not doing any good. It's got a hole in it. So I got me a ball of solder, and I stopped up that screen. You know, after that tractor, you could have it set where the gallon of fuel is supposed to remain in the tank, and when it quit, it was empty. You switch it over, and it still wouldn't run. You couldn't get home. You had to walk home. Well, it turned out that they had put that hole in there as a vacuum breaker to break the vacuum on it, and that is the way that the shuttle system works. The screens that we have in there is fine enough so that the surface tension across those small pores is strong enough so that it'll keep the air from punching through unless you put a big hole in them. So we had to make sure, and that was another one of the things that convinced me that we could design a screen system that would work in the absence of gravity.
Goes back to a Ford tractor.
Goes all the way back to 1947 and a Ford tractor.
Henry, okay, well, we've come to the end, so let's thank Henry for